right, so day 3, yesterday or Friday, we looked at what are the properties of parallelograms. So in this case, you were given a parallelogram, and once they told you, hey guys, this is a parallelogram, all of these properties were true. Okay, so today we're going to give you a figure, but it's not going to have any markings. It's going to have some markings on it. They're not going to tell you this is a parallelogram. You're going to have to decide, is it? It looks like a parallelogram, but is it really a parallelogram? Okay, so there are 5 theorems that we can use to show that a quadrilateral is a parallelogram. So we're going to go through those 5, and then we're going to apply them. So the first one says, if both pairs of opposite sides are parallel, then the quadrilateral is a parallelogram. So if you look at a quadrilateral and you see markings that show this side is parallel to the opposite side, and this side is parallel to its opposite side, then we know we have a parallelogram. And so even though it's not marked, I know my opposite sides are congruent. I know my opposite angles are congruent. I know my consecutive angles are supplementary. And I know my diagonals bisect each other just from those 4 markings. I know all of that other stuff is true. And again, this was both pairs of opposite sides parallel. Okay? When I look at the next one, it says both pairs of opposite sides, so it starts out exactly the same, both pairs, opposite sides, but this time, congruent. So this time when I look at my picture, instead of seeing that my opposite sides are parallel, I'm going to see that my opposite sides, those 2 are going to be congruent to each other, and then these 2 will be congruent to each other. Yes? Okay. So if I can prove that those sides are congruent, or if it's given to me that those sides are congruent, or that both of those pairs are congruent, then I know, even though it's not marked, when I look at this picture, I know opposite sides are parallel. I know opposite angles are congruent. I know consecutive angles are supplementary, and I know diagonals bisect each other. I do want to kind of come back up to this one real quick. So on this one, I said if you're given a picture like this and you can see that your opposite sides are parallel, or your top and your bottom are parallel, both pairs have to be parallel. Sometimes they're not going to give you the markings there. You can prove it though. So if you can show, right, this is all about proving parallelograms. If there's a way to prove or to show mathematically that you have parallel lines, so for example, on a graph, if you can show that these 2 have the same slope as each other, so they're parallel. If these 2 have the same slope as each other, then they're parallel. So on a graph, you could compare slopes, right? Sometimes you'll have diagonals drawn in, and they'll give you some angles on those diagonals. And that's to help you prove things are parallel. Because if I go way back to Unit 2, Day 12, we learned that if parallel lines are crossed by a transversal, then the following theorems are true. And then we talked about the converses. We said if your corresponding angles are congruent, then your lines are parallel. If alternate exterior angles are congruent, then your lines are parallel. If alternate interior angles are congruent, then your lines are parallel. If same side interior angles are supplementary, then your lines are parallel. These last 2 will get used a lot in this section because we will end up with some alternate interior angles. And if we can show that they are congruent, then that means even though my lines across from each other aren't marked parallel, using the alternate interior angles converse, we can prove that they're parallel. Or if I have 2 angles on the same side of a parallelogram and I can show that they're supplementary, then I can prove the 2 lines, the top and the bottom in this case, of my parallelogram are parallel, or in my quadrilateral, are parallel. Okay? So that would be my same side interior angles converse. So we'll use these 2 quite a bit in this unit, this idea of alternate interior angles and this idea of same side interior angles. That to help us prove that we really do have parallel lines. Okay? So again, On these examples, I'm just marking the pictures with what you need to see. Sometimes they'll just give it to you. Sometimes you'll have to be able to prove it. Okay? So you have to pay attention to that. All right, let's go on to number 3. If both pairs of opposite angles are congruent, so again, we're looking at both pairs, but this time instead of opposite sides, we're looking at opposite angles, and they are congruent. So if this top left is the same as the bottom right, and if the top right is the same as the bottom left, then I know, even though it's not marked, I know opposite sides are parallel. I know opposite sides are congruent. I know angles on the same side are consecutive or supplementary. And I know my diagonals will bisect each other. I know all the properties of my parallelogram will be true. Okay? Number 4, I do want to change what this says just a little bit. Instead of if the diagonals, I'm going to say if both diagonals bisect each other, then the quadrilateral is a parallelogram. Remember we talked about in the last lesson that my diagonals don't have to equal each other, but they should be bisected. So that means when I draw them both in, one diagonal is cut into 2 congruent pieces, and the other diagonal is cut into 2 often different pieces, but the same to each other. Okay? So if you can show that, again, I'm not showing that the diagonals equal each other, I'm showing that they've been cutting in half. So if I can show that my diagonals have been cut in half, then I can say I have a parallelogram. So my opposite sides are parallel, my opposite sides are congruent, my opposite angles are congruent, and my consecutive angles are supplementary. Okay, all the things. And then last but not least, this one is like the weird different one, because everywhere we said if both pairs, if both pairs, if both pairs, if both diagonals, and now all of a sudden we're just looking at one pair of opposite sides is both congruent and parallel. So that one pair has to do both of those things. We have to be able to show mathematically, or it has to be given to us that they are congruent, and that one pair that's congruent also has to be parallel. If we can show that, if it's given to us or we can show it mathematically, then we can say that this is parallel and my opposite sides are parallel, my opposite sides are congruent, my opposite angles are congruent, my consecutive angles are supplementary, and the diagonals bisect each other. Okay? For this lesson and for this class, I will let you refer to these theorems without having to write the whole thing out. But this is just the order I happen to teach them in. Some other teacher might teach them in a different way, so you might not be able to use these theorems. Here in Marshall, everybody uses these same notes, so all the geometry teachers would have these in the same order. But we're just going to refer to these as Theorem 1, 2, 3, 4, and 5, just to save us a little writing time. But again, if you were to, let's say, tomorrow you found out, oh, I'm going to O'Connor now, and they were doing the same lesson, they might not refer to this as Theorem 3, right? So you might have to write it out. Just keep that in mind. All right, so we want to prove, can we prove that the following quadrilaterals are parallelograms? I'm going to zoom in because y'all can still see the 5. We want to say which theorem we're using if we say yes. So number 1, can I prove that that's a parallelogram? Yes. Yes. By which theorem? 5. By 5. Because 5 says opposite sides are parallel, which we can see, it's marked for me. And opposite sides are congruent. It's not marked that they're congruent, but it's marked that they're both 12, so they have equal measures. And the definition of congruent is equal measures. So they are congruent. Okay? What about number 2?
Yes.
Yes? Which one? 2 says opposite sides, both pairs of opposite sides are congruent. So I can see these 2 are marked congruent. And I can see these 2 are marked congruent. So 2 questions, 2 follow-up questions for number 2. Is a square a parallelogram? Yes, because opposite sides are congruent, right? Is number 2 a square? Who said no? You're the winner for today.
Thank you.
You're welcome. Why can't I say number 2 is a square?
Because it has to be showed.
It has to be shown, right? And what other property do I need shown to know that that's a square? I need 90-degree angles. Do you know what we could call number 2?
A parallelogram.
It is a parallelogram, but there's actually something even more specific that we're going to learn later. Anybody know? I think we're going to learn it on Thursday. It's what? A rhombus. It's a rhombus. It's a rhombus. A definition of a rhombus is all my sides are the same. If you look at the tree on the front, right, we have parallelogram, and then my parallelogram splits off over here to rectangle, which we know has 90-degree angles, right? And the rectangle is a parallelogram. And then my parallelogram splits off into rhombus. All the sides are the same, but then look at these 2 branches. They come back together and make a square. So the square is really a rhombus and a rectangle, like growing together. Okay? All right. Let's move on to number 3. What about number 3? Yes or no? No. I have a set that's congruent and I have a set that's parallel, so it's tempting to go with number 5. But because it's not the same set that's parallel and congruent, it's the sides that are congruent and then the top and bottom are parallel. So that's going to be a no. I can draw something that has parallel sides and the other 2 sides are congruent. That's not a parallelogram. Do you know what it looks like? If 2 sides are parallel, and then the other 2 sides are congruent, what could it be?
Trapezoid.
Oh, it could be a trapezoid. We'll get there, I think, on Monday. We'll get to the trapezoid. This is specifically called an isosceles trapezoid because its legs are congruent, just like an isosceles triangle. It has congruent legs. So does an isosceles trapezoid. Okay, number 4, AC is 25. So from A to C, that's this length here. And BD is 25. So this whole length right here is 25. Is that a parallelogram? Yes or no? No. The only theorem we have about diagonals say if both diagonals bisect each other. So until they tell me that this piece is 12.5 and this piece is 12.5 and this piece is 12.5 and this piece is 12.5, I don't know that that's a parallelogram. Because I could come back to this trapezoid and guess what one of the properties of an isosceles trapezoid is? It is that these diagonals are congruent. But this piece here will not be congruent to this long piece right here. It will actually be congruent to this piece over here. And then same down here, this piece will be congruent to this piece. In an isosceles trapezoid. So congruent diagonals is not enough to prove a parallelogram. Congruent diagonals is not enough to prove a parallelogram. They have to be bisected. So this is no. Number 5. Yes or no? Yes, which theorem? 3. 3 says both pairs of opposite angles are congruent. Are these the same? Are these the same? Yes, so my rectangle is a parallelogram. It goes off the same branch. Okay, next. What about number 6? Yes. Which theorem?
2.
Yeah, these 2 are congruent, and these 2 are congruent because they all have equal measures. What about number 7? Yes? Which one?
4.
I'm hearing 3 and I'm hearing 4 and nobody's correct. 2? Nope.
1.
I heard 5. That's a no. So the only one left is
1.
1. All right, it can't be 2 because I don't know how long any of the sides are, and there's no way to prove by the degrees how long something is. Okay, unless you have a right angle and another side so you can use trig, right? We don't have that. I can't use 4 because I don't have the whole angles. And I know it's real tempting to go, well, if this side's 42, this side's 42. But no, we talked about that the other day. I think, did I draw this in this class the other day? No, I must have drawn it in 6th period. So if you look at this rectangle, we already discussed that a rectangle is a parallelogram. Look at the diagonal. Does it cut this angle into 2 equal angles? No, this one is clearly much more acute than this one, right? I have never once said diagonals cut an angle in half. So in a parallelogram, you can't assume because one angle's 42, the one next to it's 42. Because one angle's 45, the next one's 45. In fact, that wouldn't even work out because if these two were 45s, then I'd have 90 degrees here and I'd have 90 degrees here. And if these two were both 42, then I'd have 84 here and 84 here, and I wouldn't add up to my 360. So these are definitely not bisected. But if I were to think of the top and the bottom as lines, and I were to think of this as a transversal, what do we notice about the two 42-degree angles? They're alternate interior. And according to the alternate interior angles converse, if alternate interior angles are congruent, what does that mean about the two lines that they go between?
Parallel.
They're parallel. Remember I told you at the beginning of the lesson this would become important to remember. And the sides that are parallel, it's real tempting to go, oh, it's also the sides using those 42. But the 42 is touching this transversal, and then it's touching the top and it's touching the bottom. So that's how I knew the 42 went with the top and the bottom. When I look at the 45, that's this transversal, and it's touching not the top, it's touching the side here. And this 45 from the transversal is touching this side here. So what do I know about the left and the right side if both the 45s are congruent to each other?
Parallel.
The sides are parallel. So, which theorem are we using to prove this? Theorem 1. Because we can see that both pairs of opposite sides can be proven to be parallel. Alright, and then number 8, the last one. Yes or no? It's not a trick question. Yes. By which one? 4. Both of my diagonals we can see are cut in half. The one diagonal is 32 and it's been cut into 16 and 16. The other diagonal is 14 and it's been cut into 7 and 7. So they both have been bisected. Okay? Alright. Questions on 1 through 8. Be careful on ones like these, right? Sometimes we have to just use our previous knowledge of math, of geometry, of all the other 6 units we've done prior to this one. That one went all the way back to Unit 2. All right, what values of x and y would enable you to prove the quadrilateral is a parallelogram? So on this one, I have information about the side lengths. So which theorem, 1, 2, 3, 4, 5, should we be trying to prove on number 9? We're trying to apply. 2, right? I want to show my opposite sides are congruent. So if I can show that the 2y and the 8 equal each other, and the 2x minus 2 and the 12 equal each other, then this would be a parallelogram. How big is y? How big? 4. How big is x? 7. right? 2x equals 14, so x equals 7. Now, they didn't tell me that this is a parallelogram. It said what values of x and y would enable me to prove that this was a parallelogram. So we're going to say if y equals 4 and x equals 7, both of those things have to happen, then it is a parallelogram. We don't have any way to prove that any of that's true. But if it happens, then it's a parallelogram. If x is anything else, and or if y is anything else, then we're no longer a parallelogram. Okay? All right, number 10. Which theorem do you want to try for number 10? 3. Both pairs of opposite angles are congruent. It's going to be easy to show that with the 11x and the 55. Right? I need to show that these are the same. So that's easy. I just divide by 11. And what does x need to equal?
5.
X needs to be 5. And then I'm trying to prove, it's real tempting to use my idea of my consecutive angles here, but that's not part of the property. The property is opposite angles, so I need to work with these. So I need to use other things I know about a quadrilateral to figure out how big those opposite angles should be. How many degrees in the whole quadrilateral? 360. Minus, I've used 55 here and 55 here, so I've already used 110. So that leaves me with 250 left for these two angles, which I know need to be even. They need to be the same. So I need to take that 250 degrees and divide it equally in half. How big do those opposite angles need to be? They both need to be 125. So 5y needs to equal 125. So how big does y need to be? 25. So if x equals 5 and y equals 25, then it is a parallelogram. Alright, number 11. Which theorem do you think we're going to try on number 11? 1, both pairs of opposite sides are parallel. So I can show that if I look at this angle here that has the 45, which touches the transversal and this side, and this 9x, which touches the transversal and this side. So I know that if the 45 is equal to the 9x, then I know that those two sides are parallel. But I don't have any information to be able to prove the top and the bottom are parallel. I can only prove the left and the right are parallel. So number 1 is not going to help me for this one. What other theorem do you think? What other one has parallel in it? Which one? 5. Can I prove I have those right and the left are parallel? Would I be able to show that the right and left are congruent? Yeah, they both need to equal 18, right? If I can show that 6y equals 18, then by theorem 5, this would be a parallelogram. So when I solve the first one, that's easy, we just divide by 9. And when I solve the second one, that's easy, we just divide by 6. So it's all division, property of equality. How big is x going to be? 5. How big is y going to be? 3. So if x equals 5 and y equals 3, then it is a parallelogram. All right. Questions? Okay. Let's look at the next one, parallelograms on the coordinate plane. Determine whether ABCD is a parallelogram. So A is at negative 2, 3. B is at 3, 2. C is at 2, negative 1. And D is at negative 3, 0. And remember, when you connect the dots, you have to go around it like it's hot lava, starting at A. So you start at A, and then you go to B, and then to C, and then to D, and then you get to go back to A. Don't fall in the lava. All right. So I can try to prove that this is a parallelogram using either one. Both my opposite sides are parallel by just comparing the slopes. If the rise over the runs are the same for these two, and the rise over the runs are the same for those two, then this is a parallelogram. Or I could apply the distance formula or Pythagorean theorem to find out how long these two are, and then how long these two are, and if these are the same as each other, and these are the same as each other, then it's a parallelogram. Theorem 3, trying to prove angles on this one, not so fun. We don't have the tools yet to do that, so we'll not do number 3. Number 4 we could do. For number 4 we could draw in this diagonal, find its midpoint, draw in this diagonal, find its midpoint, and then use the distance formula 4 times. 1, 2, 3, 4 times to make sure the first two equaled each other and make sure the second two equaled each other. That's a lot of work. I don't want to do that one. But we could. And then number 5, picking one pair of sides, so either these sides or the top and the bottom, and saying, do they have the same slope and do they have the same length? So Pythagorean theorem or distance formula. And then that's all I would have to do. Or the same thing, I could prove that these are parallel and the same length. Personally, I think number 1 is the easiest because all you have to do is compare rises over runs. And if they all match up, yay, it's a parallelogram, right? So if I just compare the left side to the right side, and I look at the slope from A to D, and the slope from B to C, if they're the same, then those two pieces are parallel, right? What's my rise over my run to get from D to A? How much am I rising? 3. How much am I running? So 3 over 1, or 3. From B to C, how much am I rising?
3.
How much am I running?
1.
So it's also 3 over 1, which is 3. So these are parallel. Okay, then let's check A, B, and D, C. Make sure it's not a trapezoid. Because one set of parallel lines gives me a trapezoid. I need 2 sets of parallel lines. So I need to check the slope of AB and the slope of DC. I can tell they're negative because they're both going downhill. So they're both negative. How much am I rising to get from A down to B? How much? I'm going down 1. How much am I running? 5. So negative 1/5, that doesn't reduce, it just is negative 1/5. From D to C, how much am I going down? 1. How much am I running? Also 5. So down 1 over 5. Are they parallel? Yes. So this is parallel to this. Is this a parallelogram?
Yes.
Yes, it is. A, B, C, D, is a parallelogram. I don't know why I put a big space between parallelogram. It's a parallelogram. Okay? When you have a coordinate grid, that's going to be the easiest way to show you have a parallelogram with the less amount of actual algebra involved. Okay? All right, let's look at our favorite thing ever to do, because I know it's been a while, so you've been missing them. We're going to do a proof. I know. Given all of those angles equal all of those things, can we prove quadrilateral JMHS is a parallelogram? So when I sketch my picture, because they didn't give me a picture, when I sketch it, I'm going to sketch it like it is what I'm trying to prove it is. So I'm going to sketch myself a parallelogram. I'm not going to mark it as a parallelogram because I haven't shown that it is. And then as I prove things, I'll mark it as we go. So we're going to pick one corner to start labeling in. Where do you want to start?
Top left.
Top left. That's where I always like to start. And then remember, you have to label it like you're walking on the edge of hot lava, and you can't go across the figure because you'll fall in the hot lava. So we have two options from there. We can either go to the right and put our M on the top right, or we can go down and put it on the bottom left. Do you want to go to the top right or the bottom left?
Right.
Okay. I usually go clockwise too. So the only thing we can't do now is we can't put H over here. I can't go JMH because I have to go through the hot lava then to get to H, right? So we have to go around the figure. JMH has to go down here, and then S has to go over here. If you put your H over here, then all of these angles are going to be in the wrong places, and it's not going to work out, okay, because you didn't label the correct quadrilateral. Okay, so given angle MJH is 24 degrees, so we should probably put that in our proof, right? Measure of angle MJH is 24 degrees. That is given to me. Now, I want to add that to my picture, but MJH is like inside. I have to draw in this diagonal to see that angle. MJH is this angle right here, 24 degrees. Okay? There's really not a whole lot I can do with that except know that that's there. So I need to look at my next given. I like to check them off as I put them in the proof. My next given, the measure of angle JHS is 24 degrees. That is given to me. Let's look and see so we can add that to the picture as our given. JHS, so that's going to be down here where H is the vertex, and it goes off to J and off to S. Since they're both equal to 24, before I go to my next given, I'm going to go, well, those are congruent to each other, right? They're equal to each other. They're both 24. So MJH, the measure of angle MJH, is equal to the measure of angle JHS. So where I start with the measure of angle MJH right here, it's supposed to be equal to 24. But I didn't say it was equal to 24. I said it was equal to what 24 equals. What did I do to be able to replace this 24 with this angle? Substitution. Replacement and substitution, same thing, right? Then I'm going to look at those angles and go, well, what kind of angles are those? They are alternate interior angles. Angle MJH and angle JHS are alternate interior angles. And we know that not because of the picture, because we drew the picture, right? We know that because we know what the definition of alternate interior angles are. They're angles on different sides of a transversal between two lines, right? Not between two parallel lines, but between two lines that are crossed by a transversal, right? Which we know is happening. So this is by the definition of alternate interior. Oh, so now I have two congruent alternate interior angles. What does that tell me about this picture? I have parallel lines. Which lines are parallel? Yeah, remember, so from the transversal, if I go across that angle, it'll show me what line I'm working with, right? JM. And if I go from the transversal across that angle, HS. So JM segment is parallel to HS segment. Do you remember what I said we're going to use for our reason? from back here on day 12? Almost. You're missing one word on the end of it. Alternate interior, not exterior, angles, converse. Alternate interior angles, converse. I got all of those lines, 1, 2, 3, 4, 5 lines, and I only used 2 givens. I still have 3 givens left. Let's look at the next given, see if there's anything we can do with it. My next given is the measure of angle MHJ is equal to 30. I'm going to add that to the picture and see if there's anything I can do with it. MHJ is equal to, that's this angle here, is equal to 30 degrees. So there's really not a whole lot I can do about it unless I just wanted to show you how big I could use angle addition and show you how big MHS is, but I don't know that I'm going to need that, so there's really not a whole lot to do with that. So let's go on to the next given. I'm going to check mark that I put that there. The measure of angle HJS, HJS, is equal to 2x. Given. And I'm going to add that to my picture. HJS, HJS. Now, last time I wrote the 2 angles, and I went and said that they were equal to each other, but I don't know if they're equal to each other or not, because one's 30 and one's 2x. But I do know how I could classify those angles in relation to each other. What kind of angles are those in relation to each other? Exterior? Interior. We don't have any exterior angles on our quadrilateral unless we extend some lines outside. So angle MHJ and angle HJS are alternate interior angles by the definition of alternate interior. And last time after that, well, then I said I had parallel lines because I could say, well, this goes with JS, and this from the transversal across it goes with MH. So I should be able to say that these are parallel, but we only were able to say they were parallel because those 2 angles were equal. We have not said those 2 angles are equal yet. So I still need to say those 2 angles are equal, which I haven't done yet, but I have one more given. If one last given, the last given is x equals 15. What can I do with that? I can substitute it in right here for the measure of angle HJS. And then I can simplify 2 times 15 to see that that is 30. Simplify. So now what? Set them equal to each other. Measure of angle MHJ is 30, and so is the measure of angle HJS. So if they're both equal to 30, then they're equal to each other by substitution. So now we've proven that these 2 angles are congruent to each other, and we've proven that they're alternate interior. So they are alternate interior angles that are congruent to each other. So that means I have what? Parallel sides. My side to JS, the left side, is parallel to MH, the right side. What am I going to put for my reason? Alright, so now look what I've shown. I've shown the top and the bottom are parallel. I've shown the left side and the right side are parallel. So since I've shown all of that, both pairs of opposite sides are parallel, right? Both pairs of opposite sides are parallel. Which theorem is that? So theorem 1 says I have a parallelogram. JMHS is a parallelogram by theorem number 1. Which in any other class you couldn't just put theorem number 1 over there. You'd have to put both pairs of opposite sides are parallel. Questions? All right. Your assignment is available to you in Schoology.